Good.
Oh, okay, cool.
Yeah.
Yeah.
Uh,
No, you just got this. Is that on the chat? Oh no, that's showing.
Yep.
Oh, it's gone now.
Yeah.
It's fine. No, look what you've done.
It's gone.
Yeah, only because I'm back there. If I need to interact, it's all gone wrong. How do we get rid of that?
There.
Hide me. Ah,
I think it's fine.
think it's fine?
Yeah. Nothing get in the way of my.
So disappointing. Anyway, yeah, thanks, Bastiano. So I'm just doing a short hour-long talk. Sort of the aim is to give a bit of an overview of statistical physics and the sort of language that we use. But obviously, I'm not just going to go through a list of nomenclature. So it's focused a little bit more on my broad research area, which is sampling algorithms for phase transitions. But statistical physics isn't restricted to just this, but as a large, it's one of its most significant focuses, and throughout the course of the masterclass, you'll see some other areas that people tend to be interested in. But I will start with some notation. So first of all, I'm going to denote R as a vector representing the state of the system. So each of the so we have n particles on some d-dimensional space, and the position of each particle is denoted Ri, and it might have components xi, yi, etc. for depending on the dimensionality of the space in which it exists. So these r's are some n times d-dimensional vector. Pi r beta theta is the Boltzmann distribution. So this beta theta are hyperparameters that we're not sampling over, which sample over the r's. And this beta, you're probably familiar with it, is proportional to 1 over the temperature, and it's something called the inverse temperature. That theta is a vector of additional hyperparameters. So that might include the volume or the pressure applied to the system. Don't need to worry too much about what that means. Expectations, I'll denote a bit like you do, expectation of f, and this is equivalent to this always denotes an expectation over the r, so over the particle position, so over the parameter, but not over the hyperparameters beta and theta, but they might sometimes appear as a function next to it. I don't do this, but you might see this in statistical physics papers. People sometimes denote expectations in this strange sort of inner product notation. So you might see inner product. Sorry, you'll see on Thursday. It's always obvious that it's not an inner product because you haven't got two things in it. So, but yeah, just be aware that it's not a norm or anything like that. And F bar typically denotes the time average in statistical physics, although I don't think I use that there. Yeah, and just as Sam said, just stop me at any point if you have any questions. Before we move on, it's also important to it might not be in the way. I need to get rid of this. I can't interact with it on here though. No, it's just. I can't interact with it at all. That's the problem. Maybe I'm going to stop sharing and go back. Or should we just live with it? It's fine, isn't it? Yeah. Okay. Yeah. So these so the positions R might correspond to multiple different things depending on the model that you're interested in. So you might all be familiar with the 2D Easing model. I'm guessing most people here know the. No. Okay. Some people. So the 2D. I'll talk about it throughout the rest of the talk. But the 2D Easing model looks like this. These up-down spins denote these spins denote these up-down spins basically take values. If the arrow is pointing up, they take a value of +1. If they're pointing down, they take a value of -1. There's some Boltzmann probability model associated with this that I'll introduce later on. But basically, in this case, the position Ri of particle I is just an element of -1 or +1. In this case, this is something called the 2D hard disk model, which if I have time, I'll cover as well. Here we have particles existing on a shared compact manifold with periodic boundaries. So that disk here is the same as this one, and sort of wrapping around with toroidal topology. In this case, the Ri is some element of this torus T2. So there are some element of that takes some position on this compact manifold. And then they also might denote some molecular configurations if of some more complex models. So here's some water molecules or some longer chain polymer. And in this case, those sorts of models will typically be on T⁵. So you'll have a three-dimensional torus instead. So are there any questions at this point? Is that relatively clear? You can have all sorts of different configuration spaces.
Yeah, if you don't mind adding to the easing model, just to help understanding of it, you can think of each of those arrows as a little bar magnet. And we're kind of interested in how a system made up of atoms that each behave like a bar magnet would interact. Up or down.
Yeah, so I'll get on to that later. I'll talk about it a bit more detail. But yeah, basically, this is a model of magnitude. And each point on this lattice represents an atom fixed at some point on the lattice that makes up this solid material, and they each have their own tiny magnetic moment associated with it. And when they all point in the same direction, your material has a macroscopic magnetization. That's what the model's for. Okay. So I mentioned that in this case we have these particles existing on a compact manifold with toroidal topology. So we have periodic boundaries. It's also the case with lattice-based models. So these lattice-based models tend to be used in what we call hard condensed matter. So that's studying the physics of solid materials and understanding how in this solid material the material responds to some external parameters like your external magnetic field or the temperature or whatever. In this case, these models are typically used in soft matter. And so they're used to understand how a substance might change between its liquid, solid, and gaseous phases as you change the temperature, pressure, and volume of the system. But in both cases, so I've already explained that this has toroidal topology. We also have toroidal topology here. But instead of applying to the configuration space, it applies to the lattice. So these spins along here are neighbours of these spins here, and it's the same here. So there's no actual there's no boundary in this case of toroidal topology. If I tell you that in statistical physics, we're typically interested in understanding the macroscopic properties of these models, the macroscopic properties of some experimental systems using these models, can anyone hazard a guess as to why we apply periodic boundary conditions? It does help with that, yeah. You have it's much easier for your space analysis. But it's something more fundamental. So basically, if you were to include, if rather than having periodic boundaries here, so if rather than this particle moving through this boundary, it bounced off the boundary back into the bulk of the system, this would introduce very strong boundary physics, very strong boundary effects to the physics of the system. But what we want to do is to simulate the physics of small windows inside the bulk of a very large system, and then progressively increase the size of the system to develop or support scaling arguments to the large n limit, because this large n limit reflects the macroscopic physics of these macroscopic systems that we're interested in. So we typically apply these periodic boundaries to get rid of the boundary effects so that we can better capture the macroscopic physics that we're interested in. Okay. Okay, so that was a little intro with some notation and a few things like that. So first one, I'm going to start with the similarities and differences between Bayesian inference and statistical physics. I'll then move on to phase transitions and how this can induce slow mixing, and I will present this using the example of the 2D Ising model, which I just sort of touched on earlier. And then they'll use this to motivate the development of the Wolf algorithm, which was a sophisticated sampling algorithm that was developed to circumvent slow mixing in the Ising model. And then if I have time, I might not, because I've only got an hour, I'll move on to continuous state spaces and hopefully some description as to how ECMC has some analogies with the Wolf algorithm in that it was developed in response to slow mixing for systems on continuous state spaces rather than on discrete lattice, rather than for discrete lattice space model. And just quickly, ECMC is the acronym for Event Chain Monte Carlo, which is a piecewise deterministic Markov process, which I'm guessing quite a lot of you have heard about as you're at Warwick and Bristol. Okay. Okay, so basically, so I suppose the first place to start with, what exactly is it that statistical physicists do, and what are the similarities and differences with Bayesian statistics? So at a high level, the goals within each discipline are pretty much the same, and that's to sample from and estimate statistical expectations with respect to some usually quite challenging probability distribution pi, which in our case is this Boltzmann distribution. Yeah. Okay, so whilst both research fields aim to simulate or sample from such distributions, often, as you'll all be quite aware of, the nomenclature can be quite different, but also the methods of explanation and I'd say the key goals can differ quite significantly as well. So from the Bayesian side of things, Bayesians tend to, a practitioner in Bayesian inference will typically fix the hyperparameters or potentially also sample over them, and then encode the input data Y by the likelihood, and then aim to, where the aim is to fit this input data to some probability model essentially, and then predict statistical expectations with respect to the parameter X. So sometimes I know that you don't always just fix beta theta, so you might include that in, if you're sampling over, I'm including it in the X essentially. However, in statistical physics, models are typically defined independent of input data, and expectations are instead studied as functions of the hyperparameters beta and theta. So as I said before, this beta is the so these beta and theta become what we call thermodynamic parameters, whereas I said before, this beta is the inverse temperature. So you might be interested in some temperature range, so some region in thermodynamic hyperparameter space where we're going to see something like a phase transition occurs, and then you might fix multiple values of your inverse temperature, sample each of those values of the inverse temperature to estimate statistical expectations of all those different values of beta, and then use those results to study that statistical expectation as a function of beta. So then you can see how these expectations vary through thermodynamic parameter space. Okay. Okay, so the reason that
you basically said that you vary beta and theta, and you see how expectation changes.
Yeah, exactly. Yeah, exactly. But to do that, what you're basically doing is you'll fix an array of beta. For example, you fix an array of beta values, sample over R the positions at each of those beta values. So you'll perform your sampling algorithm at each of those beta values, and then you'll study the outputs for those different beta values. And so, because the aim is essentially to be studying how that expectation varies as a function of beta. Sometimes in physics, people also have input data that goes into the model, but it's not sort of very much non-standard. Like people, most of the time, you have some model that you're interested in, and you just want to sample from that model. Okay. So one example of what might happen is you vary your so as you vary the temperature across some phase transition, you might get a liquid to solid transition, and in this case, so let's just pretend this is some material that changes from a liquid to a solid as you vary some thermodynamic parameters. You might get the particle correlation functions changing form entirely. So as you cross this transition, so in the liquid phase, the correlations between the particle positions will typically decay exponentially with separation distance, whereas in the solid phase on long distances, you have no decay in the correlation functions, and so you get a distinct change in the behavior of this of these correlation functions as you pass through this phase transition. And then in the case of the 2D heating model, which we'll talk about in more detail in a second, it doesn't matter too much about the model at this stage. But as you go from the magnetic phase at low temperature to the non-magnetic phase at high temperature, the expected potential variance, so the expected variance in the potential per particle, which is this curve in black, it becomes strongly non-analytic at the phase transition here at 1. So this sort of non-analytic behavior is what you typically find. In fact, this non-analytic behavior is what you find at phase transitions. So it's sort of what defines a phase transition, essentially.
Say a little bit more.
Yes, okay, so ignore the red, it's just something to do with the magnetization. This is the expected, so CV is the potential variance for the variance in the potential. Sorry, expected value of CV is the expected variance of the potential divided by the number of particles n, and then in the limit n goes to infinity, it behaves like this. It means the expected value of u minus the expected value of u all squared. Yeah, so it's simple as that. Yeah. So you typically find that you get strong fluctuations in the potential at phase transitions. This is how it's characterized in this way. And it becomes, as you can see, it becomes non-analytic in this. In this case, this diverges logarithmically as you approach the phase transition bit to C. Okay. Wrong way. Okay, and so it's going to be a massively rigorous definition, but it's quite useful to sort of define what a phase transition actually is. And so to start with, we'll define a thermodynamic phase, which help to connect back with that plot we just looked at. So a thermodynamic phase is any open and connected region of thermodynamic hyperparameter space where some expectation is analytic in the large N or thermodynamic limit. So the large N limit is the limit in which is the limit of a large number of particles, and we call this the thermodynamic limit. If you take the thermodynamic limit of some expectation, if you have any open and connected region of thermodynamic phase, so thermodynamic parameter space, where this function is analytic, then that is defined as a thermodynamic phase. So if you're just looking at this function here is analytic here, so this is one phase, and this function is analytic here. So yeah, so this is each of theta. Oh, there are no additional hyperparameters in this case, so we've just got beta. Yeah, so it's just there's some fixed theta basically, and we've got beta increasing. So I'll define the model in a second, and we'll look at it in more detail.
So in ways, if you're studying a system, you sort of construct this expectation you had on the next slide, the F.
Yeah.
And in a way, you'd say, I do this, I look at how it behaves for different beta and theta. Then I chop up the space into the analytic regions, and then I give those names like liquid or.
Exactly. Yeah. So in this case, this one's called this bit's called the ferromagnetic phase. This is the paramagnetic phase.
The hydrogen model, do you, when n goes to infinity, you get the spheres to be more packed?
No, so what you do if you have a particle model, typically you'll increase n, but you'll also increase the volume. So you keep the density fixed. Yeah.
Okay.
Yeah. It almost always applies. Sometimes you get algebraic correlations, so power law correlations. But typically you only ever find, and then the law of large numbers breaks down. But typically that only happens at the phase transition. Okay. But you do get some interesting cases of power law correlations throughout a whole phase, and then things are a bit more subtle. Yeah, of course. Yeah. So that's a good point from David. Yeah, especially in quantum physics, people are often genuinely interested in like 10 particles on a ring, for example, or whatever, or on an array. So in modern physics, well, this is modern as well. In modern physics, you do also get people that are also interested in small n systems as well. Yeah, but I mean, like you then have to define a phase in the large N limit, and it doesn't really mean a lot when you have small systems. So, yeah, but that's a good point. Hmm. Okay, so that's thermodynamic phase, and then a phase transition is just some boundary between any two. So a phase transition is any region of thermodynamic phase space where you find some non-analytic behavior in some thermodynamic expectation. Okay. But the really interesting thing in terms of sampling is that when you move through a phase transition, often this will typically be in a low temperature phase, but it might be in some other phase. Some sort of multimodality develops in your potential or probability landscape. And then this leads to slow mixing under certain algorithm dynamics, and also it also happens to occur in nature as well often. And then one of the arguments is that this then informs Bayesian computation because it helps to it leads to sort of sophisticated developments in algorithm dynamics and that sort of thing. But yeah, basically you end up with this multimodality, and then in the large end, so you get this multimodality, you get slow mixing because the system might start in one well and then it takes a significantly long period of time to get over to the other well. And in fact, typically you find that the timescale for traversing this barrier diverges with diverges in the thermodynamic limit. You get what we call asymptotically slow mixing, which is asymptotically slow mixing, depending on where you're from, is sometimes called metastability, although some people say, a physical chemist might say that this is the metastable state and this is the stable state. I'd argue that there's always a finite probability of hopping between the two, so that doesn't really make sense. But people sometimes call it metastability. People also sometimes call it broken ergodicity, which might be a bit of a strange concept to a Bayesian computationalist, because the algorithms that we're interested in are always ergodic for finite n on long enough timescales. But a physicist would call an algorithm that is ergodic for finite n on long enough timescales, but which mixes asymptotically slowly, they would call this non-ergodic. And they'd say that ergodicity has been broken. And this ergodicity breaking is sometimes called symmetry breaking. So it's a bit confusing from algorithms perspective.
Sorry.
So sorry, I'm saying that this is asymptotic. So when I'm saying asymptotic, I'm saying in the large n limit. So in the large n limit, the time scale on which So in the large n limit, the time scale on which the system would traverse a barrier such as this in potential landscape, this diverges with n.
With the Markov chains, or is the mixing that we refer to Markov chains?
Yeah, exactly. Yeah. So we've talked about the two wells of the Ising model, and that it takes some period of time to traverse, to switch from one well to the other.
Yeah.
In the large n limit, the probability of switching, the probability of the system transitioning from one well to the other goes to zero in the large n.
That CV here was the variance, potential variance.
Yeah.
You said, meaning what again? The expectation.
So the expected value of CV is the expected value of u squared minus the expected
value of.
Yeah. So it's the variance of u.
So,
expected variance of u. Yeah. The expected.
What is CV then? Okay.
It's called the specific e, and because you can sometimes look at the time average rather than the expectation. It's here, but basically, expected e of CV is the expected variance of potential. Yeah, and when normalized by n in the large n limit, it's not analytic. It has I think it's non-analytic, and I know, yeah. Yeah. No, but it's still the expected variance of u. It's defined as that.
Yeah, the same thing.
Yeah.
Well,
Yeah.
Can you go back to the barrier.
So
that's beta U. Okay.
yeah, that's why I put potential here. It's not, we call the potential U, but basically, as you vary the hyperparameters, the principal one of which will be beta, you typically go from having some unimodal landscape to some multimodality as you change beta, basically.
And just another thought, I was thinking about this. So basically, U never changes, right? Use always fixed.
Yeah.
But I was thinking in terms of particles, like thinking about like Gibbs like mixtures, right? I feel like removing each individual could be similar to moving each particle, but then I feel like the landscape like changes because depending on where the clusters are located, then
Yeah.
So it's not exactly the same situation, but
Yeah.
just
thought.
We actually very rarely use a Gibson. Bigger than others, possibility distribution and a single frame. The probability distribution on the entire.
Yeah.
Can I come in for the electricity break as well? I think it's true to say that there are also examples of genuine electricity breaking, where people run Markov chains, they can get themselves into configurations that they cannot get out.
Yeah. So this is what's called weakly broken. We call this weakly broken electricity, whereas this is strong electricity breaking, isn't it? Where you genuinely completely disconnected from another region of parameter space, essentially, of the state space. Yeah. This is a pretty disconnected slide from the rest of the talk, but you might have heard. I thought it was quite useful to just mention it now. You might have heard of free energy. The free energy is just the negative proportional to the negative log of z, where z is what we call the partition function. It's just the integral over the Boltzmann factor. So this partition function is a sort of marginal likelihood. So this macroscopic free energy is just a negative log, it's a sort of negative log marginal likelihood. Sometimes people refer to beta U confusingly as a free energy as well. I'd call that like a configurational free energy. So that's just to make it even more confusing. Okay, so I touched on slow mixing there when this multimodality develops at low temperature. So I'm going to showcase that through the 2D Ising model, which I'm going to define properly and make a bit more sense. And then I'll use this as a motivation for the Wolf algorithm, because the slow mixing happens under metropolis dynamics. Okay. Stop me at any point if you need any extra pointers. Okay, so this is the plot I showed you before. We have a lattice array of up-down spins fixed at the end sites of this periodic square lattice. And then the interaction potential U Ising is just negative J, where J is just some positive real valued variable. And then the sum over this notation here, sum over inner product I comma J. You need to watch out for this inner product notation as well, because this is how I was going to write it more mathematically, but I thought this is how you see it in the physics literature. It's a good opportunity to explain it. This basically means a sum over nearest neighbours ij. So, for example, if you pick this spin arbitrarily, it's a sum over the Rij's between all of its nearest neighbours. So this Rij, this Rij, this Rij, blah blah blah. Okay, the sum over nearest neighbours, and then you're doing all those nearest neighbour sums over the whole lattice. That's what this makes sense. So the potential is minus J sum over nearest neighbours of Rij, where again those Ri's are plus or minus 1, and that J is greater than 0. So at high temperature, all the spins are pointing in different directions, and then at low temperature, the potential encourages the spins to be aligned. Okay, that's what we've got here. So low temperature, this is that high temperature figure again, so they're all pointing in random directions. At low temperature, they'll tend to be aligned, and they'll either all point up or down with small fluctuations around one of those two around one of those two modes. But often we'll have some, so n might be, this lattice might be like I don't know, often we'll go to like 256 by 256 spins. So we've got a really high dimensional spin space, really high dimensional parameter space. Does anyone have any idea as to how we would characterize this large N system? There's something that I didn't actually say, which I should have said earlier, actually, was that it's what George mentioned. Each of these, I'll go over it again now. Each of these spins represents some magnetic atom that's fixed at this point in a lattice in a lattice of some solid material, and each of these spins represents the magnetic moment associated with that magnetic atom. So it's like a tiny magnet fixed there. At high temperature, they're all pointing in different directions, and the material is non-magnetic. And then at low temperature, they all point in the same directions, and their magnetization sums to a non-zero value, and the material is magnetic. So any ideas as to how you might characterize this magnetic model in with a low dimensional statistic, a low dimensional observable? Could do with the potential. Yeah, that's a good idea. Yeah, so that's actually quite helpful, because then, as we said, the expected variance of the potential identifies the phase transition. But another way is with the magnetization. So the magnetization maps this large N model to this one-dimensional quantity. So the magnetization is just the mean value of the spins. So at high temperature, the magnetization is, I should have put approximately there. The magnetization is approximately 0, so it's most likely, most probable value is 0, and you have small fluctuations around it. And then in this particular configuration, the magnetization is 1, but this is both this and the magnetization equals to -1 are equally probable. Okay, so this is how you can characterizes this large N system with a one-dimensional quantity. It's also, like, from a sampling algorithm point of view, can anyone see why you also would need quantities such as this to actually use a sampling algorithm? Yeah, it's useful for convergence. Yeah, definitely. But it's a really simple point. If you've got 256 by 256 spins, you can't store all the spins at every point in your Markov chain. So we typically, like, if you've got a 10-dimensional state space, then you can store the whole Markov chain. But we have to map to some low-dimensional quantity and then store those low-dimensional quantities at each point in the Markov chain. So it's obviously it's not that interesting, but it's quite an important point from a physicist perspective compared to something that I think statisticians don't tend to think about. Yeah, until they run out of memory. No, but they don't, because they don't go to high dimensions. So if I just go back to that, this configuration is just as likely, it has the same probability density as all of the spins flipped, so MR equals -1. However, if you were to simulate the system using metropolis dynamics with single spin flips at each iteration of the algorithm, can anyone spot any problems that you might incur? Yeah, exactly. Yeah, for small systems, it's eventually okay. The system eventually flips, but the probability of flipping the entire system with single spin flip metropolis dynamics goes to 0 in the large N limit. And this is something that we call symmetry breaking, which is a special type of ergodicity breaking. And another way of describing it, as I've said before, is asymptotically slow mixing. So this is what happens to metropolis dynamics with single spin flips. And we tend to do a lot of our metropolis simulations tend to be in terms of single particle dynamics. Something that Sebastian and I've been discussing a bit recently, actually. It's a bit of a folklore thing in some senses. Not clear if we've inherited it, but for the Ising model case, obviously you can't evolve all spins at once, because then you just flip everything and nothing would happen. So that's why in this case we do it, but it also happens in particle models. And we think it might be because often our target distributions are functions of when you have a particle model, they're functions of the separation vectors between the particles. So if you move more than one particle at once, it's possible that you're being sort of inefficient computationally. But the question of sort of optimal particle dynamics is something that Sebastiano and I have been discussing a bit, and something we might work on in the future. Anyway, I was digressing anyway. Okay, yeah, so under single spin flip metropolis dynamics, we can end up with slow mixing, or sometimes called metastability or ergodicity breaking, which is what we see here in these two plots of the magnetization versus time. So I'm plotting that magnetization function as a function of time under single spin flip metropolis dynamics at high temperature here and at low temperature here. Just quickly, that delta T metrop, so the metropolis time step, is defined as the elapsed simulation time between n attempted particle moves. At high temperature, the system mixes symmetrically around n equals 0, so the metropolis dynamics work. At low temperature, the system chooses m equals +1, and it stays close to this state throughout the entire simulation. So it's not working, basically, from a Bayesian point of view. And the key point is that it could equally have chosen m equals -1 and then stay stuck in that state. Okay, and again, this is because the neighbours are typically aligned at low temperature. Blah, 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 blah. Just to summarize, that magnetization is the mean value of the spins. The expected value of m is 0 for all finite beta due to the spin flip symmetry of the probability density. So we should be converging on expected value of m equals 0. So this implies that the simulation mean of the magnetization goes to 0 on some time scale tau n. Oh. But at low temperature and with metropolis dynamics, this tau n diverges with system size n. And this asymptotically slow mixing is what we call broken ergodicity or metastability. Okay. So, how long have I got? 20 minutes. I'm not going to get on to the next slide. So Swenson and Wang and then Wolf decided to circumvent these problems. This is now going to be an example of how these problems of slow mixing under metropolis dynamics led to innovations in sampling algorithms, so led to the development of new sampling algorithms. So first of all, Swenson and Wang, and then it was followed by Wolf, developed what we call cluster algorithms. And these algorithms flip entire clusters of aligned spins in an intelligent way to circumvent this slow mixing. Okay. The Wolf algorithm is slightly simpler to describe, so I'm going to talk about that one here instead of Swenson Wang. But the Wolf algorithm came after Swenson Wang, and it's sort of a simplification of the first. And it basically operates by randomly picking a base lattice site and adding it to a newly constructed cluster. So what I'm describing now is one iteration of the algorithm. You then iterate. The second step then involves iterating through each of the neighboring spins and adding it to, and if it's aligned with the base spins, you add it to the cluster with probability P defined here in the second line. And you then repeat this step, step 2 for each new spin, until you stop adding spins to the cluster. So you might start here and add these 4, and then you ask those neighbors they should be added, etc., etc., etc. And then once you've finished creating a cluster, you flip this entire cluster with probability 1. And it's not too difficult to show that this converges on the Boltzmann distribution, but obviously not going to go through it here. So an example cluster is denoted here inside the inside the dashed region. So here, instead of having the up-down arrows, a down spin is denoted with the white pixel and the up spin is denoted with the black pixel. So the key point to notice is that within the cluster, all of the spins are pointing up, but there are also some spins that neighbour the cluster, which are pointing up, but that are not included in the cluster. And that's because this probability P is less than 1. Okay. And so this was found to completely circumvent this problem of slow mixing at low temperature. So these two plots are those metropolis simulation plots that I showed you before. At low temperature, it's mixing nicely around m equals high temperature. Sorry, it's mixing nicely around m equals 0. At low temperature, it gets stuck in m equals 1 state. The Wolf algorithm, which are these simulations on the right-hand side at the same high and low temperatures, At high temperature, again, it's mixing nicely around m=0, but at low temperature, it also mixes around m=0 on symmetrically mixes around m=0 on very short timescales. So this problem of asymptotically slow mixing is completely circumvented by the Wolf algorithm. It's completely flipping the whole lattice between each iteration of the algorithm.
Is this, so I know sampling algorithms aren't meant to be like an exact representation of the dynamics in reality. Do you ever see that the kind of?
Yeah, I'm really glad you asked that actually, because it's something that I would have mentioned in a physics talk, but I didn't hear. So basically, Gareth did some work in the 90s on how metropolis dynamics in the large N limit converges on overdamped Langevin dynamics, or that's its limiting process. The overdamped Langevin dynamics is something that in physics we call Brownian dynamics, and this is quite a reliable representation of the dynamics of large systems in which there's a large amount of damping, and this is the case for a lot of systems that we're interested in statistical physics. So often metropolis dynamics are quite a reliable representation of what's observed in nature. So in nature, you observe this broken symmetry. The magnet, if you have a magnetic material and it's chosen to point in one direction, it will typically take like longer than the timescale of the universe to flip to the other direction. So this problem is observed in physics. So often a physicist wouldn't view this as a problem. It's more an interesting intellectual exercise. Yeah. And what's quite an interesting point is that you can compare the output of some non-physical algorithm dynamics, like the Wolf algorithm, which correctly recreates the predictions of the Boltzmann distribution, and then compare it with some algorithm dynamics that are a more reliable representation of the dynamics you see in nature. And this is sort of quite a key characterization of broken symmetry in a way. Yeah, a good question.
The top right figure,
Yeah.
is another problem that is completely periodic. So
I was wondering actually. So interestingly, this is at very low temperature. So when you're at very low temperature, typically all the spins are going to be pointing in the same direction.
Yeah.
And this P is going to be close to 1.
Yeah.
P2.
Or 1.
Yeah, and it's 1 in the low temperature. Yeah, exactly.
Periodic marching.
Yeah, I know that's no good. But basically, when you're at low enough temperature, there are only 2 states that are valid, essentially. Yeah.
Okay.
Yeah. But if you were to move closer to the transition,
Then
it's no longer periodic. Yeah. And interestingly, also at Swenson Wang, you don't observe this completely periodic sort of behavior. This is completely just the Wolf algorithm, and it's a single spin flip metropolis dynamic. Okay, so sort of touching on that last question, this is quite an interesting intellectual point from a physicist's point of view. This is quite an interesting intellectual exercise. But usually in physics, we're interested in the expected value of the magnitude or the norm of the magnetization. So we don't really care that it's chosen m = +1 or -1 and stayed in that state. All we care about is its magnitude in any case. So it's not, from a physical point of view, it's not really a big problem, this non-symmetric sampling. However, a corollary of this broken symmetry creates some genuinely serious sampling problems at the phase transition, and we can start to look at this through these plots here. So again, these are snapshots of Ising simulations at low temperature on the left, high temperature on the right, and near the transition in the middle. And again, the black pixels represent upspins, the white ones are downspin. So at high temperature on the right-hand side, you can see that we've got complete disorder with spins pointing up and down. Low temperature, the system is mostly pointing up. As you move from high temperature to low temperature, larger and larger clusters of correlated spins appear in the system. and you get these large regions in which the spins all point up and large regions in which the spins all point down. Okay, and this yeah, so this results in these large clusters that you view at the transition here. Now this results in very strongly autocorrelated algorithm dynamics at the transition, and we can see this by thinking about these the potential landscape for the magnetization in these three regions of thermodynamic parameter space. So hidden behind this meeting thing here, so this is the high temperature. The magnetization is centered on zero and makes small fluctuations around it. At low temperature, the system chooses either m equals +1 or -1, and under metropolis dynamics, it fluctuates around one of the wells, but the Wolf algorithm can jump between the two. But in order to transition from the unimodal landscape at high temperature to the bimodal landscape at low temperature, the potential necessarily has to flatten at the transition. And so this means that you get these this means you get a very flat potential landscape, and that algorithms that are governed by the potential gradient essentially don't know what to do. They become stuck in some region of the state space for disproportionately long periods of time. And this is something called critical slowing down. So you get these large islands of correlated spins where if you look zoomed in, it looks like you're in the low temperature phase. When you zoom out, you can see that you're not. And these large islands become frustrated and stuck and don't know what to do, and essentially just become frustrated and stuck. And then you end up with very strong autocorrelations at the transition, which we'll look at now. So this is looking at this in a little bit more detail. So this was that low temperature plot from earlier. This plot here is the magnetization as a function of time, but rather than that high temperature, it's now near the transition. So it's where this critical slowing down starts to happen. Okay, so yeah, so the growing correlated clusters induce very strong autocorrelations in the trace plot of the magnetization. Now you might say this obviously looks like it's very autocorrelated, but the point is that the strong autocorrelations are with respect to fluctuations in the magnetization from its simulation mean. So here, obviously, the fluctuation from the simulation mean are zero all times, so the autocorrelation is zero. But here, the autocorrelations get very strong, and they get stronger with increasing system size. And this is what I was hoping to be able to see here. But basically, this is a plot of the integrated autocorrelation time of the Metropolis algorithm as a function of temperature. And you have to believe me that over here it's also zero, and here it's zero. And this is for an array of different system sizes, where this orange data is for the largest system size at n equals 64 by 64 system. And basically, in the region of the phase transition, the integrated autocorrelation time grows with system size. And so this divergence of the integrated autocorrelation time with the number of particles defines this critical slowing down, essentially. And this behavior leads to these strong autocorrelations mean that it's impossible to develop it's impossible to generate independent samples of your target distribution. So you get these very noisy estimates of both the expected potential variance and even the expected absolute value of the magnetization. So this was that. So at low temperature, this works quite well because whilst it might get stuck in +or -1, it's still sampling quite well around that +or -1. And this is just the absolute value. But near the transition, even this absolute value, due to these strong autocorrelations, becomes impossible to predict. And so the Metropolis algorithm completely loses its predictive power. And the reason this is important is because, certainly from my perspective, a lot of what you're interested in doing as a statistical physicist is developing sampling algorithms to better understand the physics of phase transitions, how they occur, and how you can predict them. So if you have an algorithm that works really well at low temperature and really well at high temperature, but then loses its predicted power at the transition, then you've got a problem. But basically, this is actually the more foundational reason as to why these cluster algorithms were developed. So I explained to you that there we go. So I explained to you that when you observe this, when you're at the transition and this critical slowing down happens, you get these large clusters of correlating spins. Well, these large clusters of these cluster algorithms operate by forming large clusters and then flipping them with probability 1. So you can see that it doesn't seem out of the realms of possibility that these algorithms circumvent these issues of these frustrated clusters. And that's exactly what happens. So here are those metropolis trace plots from before. Again, at low temperature at the transition, where it's broken symmetry and then strong autocorrelations. And then these are the Wolf simulations at the same temperatures. Again, that's the low temperature one we saw before. But this one at the transition is still mixing nicely around m = 0. So these Wolf dynamics circumvent these problems of critical slowing down that the metropolis algorithm suffers from. And this then results in these nice predictions, nice smooth predictions of the expected variance in the potential and also the expected absolute value of the magnetization. So all of these sort of problems are circumvented. Oh yeah, and then this is the integrated autocorrelation time. Again, the circles are the metropolis there's the metropolis output from earlier, and these stars are the Wolf, the integrated autocorrelation time of the Wolf simulations. And you can see that in the vicinity of the transition, the Wolf simulations have very small autocorrelation for all system size. They do develop this strong system size dependence at a high temperature, but this is because each iteration of the algorithm is defined in terms of creating a single cluster, and at high temperature, as all the spins are pointing in different directions, the cluster size is typically quite small. So in terms of CPU time, this doesn't exist. But in terms of the time scale naturally defined by the algorithm, it does exist. If that makes sense. Yeah, exactly. Yeah. Whereas in the metropolis case, we've defined the timescale in terms of the elapsed simulation time to attempt n metropolis moves. Whereas in this case, it's just the way the algorithm is defined. It's not a real problem. I've got 2 minutes, so I'm not going to talk about continuous state spacing. But I think Manon's probably going to cover a lot of that tomorrow anyway. But basically, you get broken symmetry, so this asymptotically slow mixing, and also critical slowing down in a lot of models on continuous state spaces. And there are strong analogies between PDMPs solving these problems and these cluster algorithms solving the problems for these discrete lattice models. But as I said, I think Manon's going to be covering a lot of that tomorrow. Yeah. As you can see, there are some nice figures. That's Manon's figure, actually, isn't it? I think it is. Yeah. That was from her PhD thesis. Yeah. I think I took them from your PhD thesis. I did credit you though, obviously. There you go. Look, Manon Michel. Can't see it. Huh? Oh yeah, just a screenshot. Yeah. I made these ones though. That was all me. That's from your paper. Yeah. And this is from my recent paper. It doesn't really matter, but this is a development of asymptotically slow mixing and then PDMPs with bias dynamics, well, with unidirectional dynamics can circumvent the broken symmetry. Okay, more on that from Manon tomorrow. But yeah, basically, I was sort of a quick rush through some nomenclature, typical notation, and then similarities and differences between our two research fields in general. And I started by making the point that Bayesians typically fix hyperparameters and they might sample over them, whereas we vary them by performing simulations at an array of different hyperparameter values to then study expectations as a function of that hyperparameter. Varying these hyperparameters induces phase transitions, as well as flow mixing, and then sometimes critical slowing down. Critical slowing down happens at something called a continuous phase transition, but not at first order. These phenomena have often resulted in physicists combating these problems with sophisticated sampling algorithms, often based on the underlying physics of the system and the problem that's been posed. If you want, you can cite my paper with Sam Livingston, which you can't see there. It's been in press for about 8 months. I don't know how long it's going to take. But yeah, I hope that was helpful, and enjoy the masterclass. How do I do that?
Stop sharing and then.
Stop sharing, stop recording, stop sharing. Can I just leave?
It's recording. Yeah, stop recording.